Okay, just to finish off looking at mechanics, just going to look at a few interesting questions that have appeared over the years, some older than others. This one, 1992, but the reason I like this one is it actually has variable angular velocity. Now, I said we only deal with constant angular velocity, and that's true, but what happens is, if you have a look at this diagram here, the train's on this circular track, and it moves around the circular track with constant angular velocity. But if we were to take a different reference point, so this point N here, and how that angle changed, that won't be constant. And so that's where the variable angular velocity comes into this question. So as I say, we've got a train going around the track, centre O, radius A, constant speed, u metres per second. N is on the same level, so it's nice and flat, x metres from the nearest point. And the line NO produced meets the track at the other side there at S, and we're given the size of the angle. So TNS is phi and TOS is theta. So the first thing they want us to do is to simply find the theta to T, so the angular velocity in terms of A and U. Okay, well, I know that the length of the arc is equal to A theta, so there's a starting point. So I can say dl to T is A times d theta to T. And there it is. So it's just that the variables they were using were strange. All they're really asking us basically is to prove V equals R omega. Because that's what we've got here, if you think about it. L, the length of the arc, we're using A for radius instead of R. And we're using d theta to T there instead of omega. But essentially that's what we've just done. Velocity is dl to T in our question. And so when we rearrange that, well, dl to T, as I say, was the velocity, which they've called U rather than V. So I get U equals A times d theta to T. Rearranging that, then I can make d theta to T the subject of the formula, and we get it in terms of U on A. Look at this wonderful one. We're going to show that A times the sine of theta minus phi minus x plus A sine of phi is equal to 0. Obvious, really. And then we're going to find this, as I say, variable angular velocity of the phi to T, this wonderful expression there. So, all right, got to prove a few things first, find some angles I can play with. So angle NTO plus TNO, that's the exterior angle, so it's going to be the same as TOS is the exterior angle. It'll equal those two added together. So I can show that angle NTO is theta minus phi. I mean, looking at what I'm trying to prove, I need to locate an angle that is theta minus phi. So that's why I did that. Okay, I know NTO is theta minus phi. Now, in that triangle, which also contains an angle phi, I'm going to use the sine rule. And so A over sine phi is equal to A plus X over sine theta minus phi. And we've now actually got the relationship they want. I just have to rearrange it and make everything equal to 0. So if we cross multiply, move everything to one side, we actually have their expression. So it was just an application of the sine rule, although a very difficult one, because do people see that straight away, that, oh, that's all it is, sine rule, go and do that. Now I'm going to differentiate. So I'm going to differentiate, well, it was A sine. Now sine, when we differentiate, goes to cosine. But I want to differentiate with respect to time. I can't differentiate with respect to time. The angle is theta minus phi. So I'm going to differentiate with respect to theta minus phi. So I have to multiply. Now, whilst I haven't written it down like this, I'm going to differentiate to theta minus phi with respect to t. So it's implicit differentiation. But remember, we have a rule in differentiation that says if we have two terms, we can differentiate each bit individually. And so that's why instead of writing it as to theta minus phi to t, I've written it as to theta to t minus to phi to t. So instead of saying I'm differentiating the whole thing, I'm differentiating each bit individually. Now I did that because of where I'm heading to. The answer I need the theta to t's and the phi to t's. And then the other term, well, that was a similar thing, but now it was only one angle. It was phi was the angle. So again, implicit differentiation. Couldn't differentiate it with respect to phi. so multiplied by the phi to t. So let's rearrange that. I've grouped the theta to t's together. Well, there's only one term with theta to t. That's a cos theta minus phi. And then I've grouped everything that has phi to t together. And so that is a cos theta minus phi, or the negative of that, and also the negative of a plus x cos phi. Remember, we're trying to find the phi to t. So I'll move them to the separate sides. Now to get the phi to t, divide by the a cos theta minus phi, and so on. So it was an awful looking expression, and I guess the trick to it was, as I say, when I'm implicitly differentiating, instead of writing the theta minus phi to t, actually writing that as two derivatives. Now, show that phi to t is equal to 0 when nt is tangential to the track. So I think a diagram is going to help here. So nt is now tangential to the track. So t's up here means that must be a right angle because radius is perpendicular to the tangent. So what other things can I spot? So as I say, NTO must equal 90 degrees. So therefore, theta minus phi is 90 degrees. Remember we said angle NTO was theta minus phi. So let's sub that in. And on the top of the fraction, I get u cos 90. On the bottom, I get a cos 90 plus, I still don't know what phi is. But I don't actually need to know what phi is, because have a look at the top of the fraction. I've got u cos 90. And cos 90 is 0. So if I've got 0 on the top of the fraction, the whole fraction must equal 0. And that's what we wanted to show, that phi to t was equal to 0. Okay, we're now going to suppose that x is the same length as a. So we're going to show the train's angular velocity about n when theta is pi on 2 is 3/5 times the angular velocity when theta is 0. Okay, so when theta is pi on 2. My triangle will now look like this because the angle NOT is now a right angle. We know OT is A. ON will be 2A because they've now said X is equal to A. So it would actually be possible to work out that angle if I wanted to. The hypotenuse is the square root of 5A. I'm not really interested in the angle. I'm more interested in the cosine of the angle to substitute in. So the cosine of the angle is 2 on root 5. The A's end up cancelling. And the cosine of pi on 2 minus phi, because that's the other one we're going to want, is 1 on root 5. So let's sub that into our formula. And we get u times 1 on root 5, a times 1 on root 5 on the bottom, plus 2a times 2 on root 5. All of that tidies up to be u on 5a. Okay, so there's our velocity when theta is pi on 2. Now, when theta equals 0, what have we got? Well, if theta equals 0, NOT, if you like, is now a straight line. So, the theta to t, the phi to t becomes u cos 0 on a cos 0 plus 2a cos 0. I suppose technically, I've said cos 0. It's really, I guess, cos pi, isn't it? It depends how you look at it, what that angle's going to be. It's flat. Either way, it's flat. So, subbing that in, we get u on 3a, or negative u on 3a, depending on whether you took it to be 0 or whether you took it to be pi. But it's more the size of the speed we're interested in. And we're trying to show one is 3/5 the other. And sure enough, one is, because that would be 5/3 of u on 5a. And so, yes, one speed is 3/5 times the other. All right. Oh, this one's a good question too. This is like a yo-yo. Remember those good old yo-yos? I haven't seen them around for a while. The Coca-Cola yo-yos you used to see every now and then. And one of the fun ones to do is to go around the world and you go, and you get it spinning and go, like in a circle. Okay, that's what this question is sort of describing. We got a string of length L, initially vertical, so our yo-yo's down here. We spun it. Mass of m kilograms attached to it. P is given a horizontal velocity of magnitude v, because we're now going to go around the world. Okay. So O is going to be the centre of that circle. A is the initial position, so it's down at the bottom there. And S is going to be the arc AP. Couldn't call it L because they've already called the length of the string L. Velocity, therefore, is ds to t in this question. Theta, the angle it sweeps out, AOP. Tension in the string is T. And acceleration due to gravity, G. So standard sort of things. And we're going to assume there's no frictional forces acting between the yo-yo and the string. So for parts A to D, assume the mass is going, in fact, in that nice circle where we're doing our around the world and it's working. So we're going to show that the tangential acceleration looks terrible. But if you look at it really closely, it actually is something very familiar. And that is acceleration of d dx of a half v squared. Difference is, we're talking about angular, and this is where the length of the string is going to come in. We're going to have to do some converting in here. So let's start with that. S is equal to L times theta. So velocity is ds to t, which will be L times the theta to t. So the acceleration is dv to t. And I'm going to do exactly what I did before all those weeks ago when we proved d dx of a half v squared. I'm going to use the same idea. So I've changed dv to t into dv to theta by d theta to t. But d theta to t in this case is v on L, whereas before when we did it was just v. So I've taken out the constant 1 on L out the front because we want that. And so now I've got dv to theta times v. But v I can rewrite as d to v of a half v squared. So the dv's cancel, and there it is. So exactly the same technique that I used when we proved d dx of a half v squared. You can see why that's considered a harder 3-unit question, I guess, if you like. All right, so show that the equation of motion is 1 on L d to theta half v squared equals minus g sine theta. Oh, well, let's start resolving our forces. So horizontally, I'm going to assume I'm at a point where the tension is horizontal. So I'm looking at it as if the tension is horizontal. But it now means that gravity is at an angle. Now, vertically, mg sine theta will be going down. But what we do know is the resultant force is minus mg sine theta. However, we've just found an expression for s double dot, or the acceleration linearly. So s double dot is minus g sine theta. So if I sub in that expression we just proved, there it is. 1 on L d to theta of a half v squared is minus g sine theta. Now we're going to deduce that capital V squared is little v squared plus 2gl 1 minus cos theta. Okay, we've just proven that. So there must have been a reason for it. Let's play with it. So I multiply by L. I now have d to theta. But it's in terms of theta. So I don't have to do anything fancy here. I can just integrate with respect to theta. And I get a half v squared as gl cos theta plus some constant. Multiply through by 2. And that's looking good because I've got a 2gl over there. Now, some initial conditions. We said that when theta was equal to 0, we're going to send it off with a velocity of capital V. So from that, we can work out our constant is capital V squared minus 2gl. Sub that in, and then it's just a little bit of playing with the algebra, rearranging it to make it look like what they want us to get. So it's got V squared plus 2gl outside of 1 minus cos theta. Okay. Explain why t minus mg cos theta is 1 on L mv squared. So now it's looking at the other forces. So, all right, tension, and we'll have mg cos theta. So the ones that look horizontally. And our resultant force will be going inwards, but that is going to be our centripetal force, because that's the one that's going along the radius to the centre of the circle. So mx double dot will be t minus mg cos theta. Well, as I say, but that resultant force is the centripetal force. So it'll be mv squared, well, normally on r, but we're using L for the length of the string. So mv squared on L. And so rewriting that, we get the expression we want. T minus mg cos theta is 1 on L mv squared. All right, so now for the fun question, part E. Okay, suppose that v squared is 3gl. We're going to find the value at theta when tension is equal to 0. So I now know that T minus mg cos theta is 1 on m, but instead of writing v squared, remember we just showed v squared is capital V squared minus 2gl and so on. But tension is 0 for this problem. And v squared is 3gl, so I've substituted both of those in. Remember, we're trying to make theta the subject. We're trying to find the angle. So, okay, minus mg cos theta is now equal to, well, I can multiply by L, gets rid of the L's there, and we've just got g plus 2g cos theta. So 3mg cos theta is minus mg cos theta minus 1/3. That's about 1.911 radians. So consider that situation. They want us, and this is the bit you hate, words. This is not English. Briefly describe in words the path of P after the tension becomes 0. Okay. What's going to happen is, as soon as tension is 0, it's like the string's no longer connected. So what's going to happen to our yo-yo? It shoots off. It's like we've just done a projectile motion question, because we've given it an initial velocity at that point when t equals 0. It's now in free fall. And we know when an object moves in free fall but at an angle, that creates projectile motion. So it starts going underneath. It's going to move a parabolic arc. So the initial velocity of this projectile motion would be at tangent to the circle at that point, because it's just as if we'd cut the string. The yo-yo goes off at a tangent to the circle. And again, I might have gone overkill here. And I've worked out what that initial velocity will end up being by substituting, and it works out to be the square root of GL on 3. Whether they were expecting all that or not, I probably not. And then I thought I'd draw a picture as well. Okay, so it started at the bottom, and after 1 point, so somewhere up here before it's reached the top, but after it's reached quarter. The other reason I know that is because we said cos was negative 1/3. So at that point, it's going to go projectile motion, shoot off in the direction of the tangent, become a parabola. But then it'll get to a point where the string will kick in again. And as soon as the string kicks in, it'll go back into circular motion. And it's like that wobbly yo-yo, when you didn't quite get around the circle, around the world correct. Imagine it, I wish I had a yo-yo here. I could demonstrate it. You know the situation I'm in where you're trying to do it and the string goes slack and it looks like, it just drops. But what it's really doing is a parabola. And then the string kicks in again. It's going back in a circle. That's what's happening. That's what's happening here. Ta-da. I like that question, the yo-yo question. All right, here's a good one too. We do projectile motion in 3 unit, but in 4 unit we start talking about resistance. And this combines the two together. So we've got projectile motion, but we've got to take air resistance into account. So the path of the particle is no longer a perfect parabola. Okay? So this is what we've got here. We're throwing from the top of a tall building, initial velocity u. So typical projectile motion question, but they've added in not only gravity, it has a resistance, and that resistance is going to be proportional to its velocity. Okay? So to help us out, they've given us the equations of motion. We didn't have to derive them for this question. So horizontally, we'd end up with minus k x dot, and vertically we get minus k y dot minus g. You are not... Make sure you read these little hints. A lot of people waste a lot of time. They go, what do they mean, not required? No, I'm going to do it anyway. Okay, it's a waste of time. derive this result. So the horizontal velocity, they're telling us, turns out to be ue to the power minus kt cos alpha. Let's derive it. Okay. We know acceleration in terms of velocity is minus kx dot. I want to end up with, and it looks horrible, but when you look at it, the only variable on the right-hand side is t. We're setting off with a constant alpha, use the initial velocity, k is a constant as well. So really what we're saying is I want to get velocity in terms of time. So for acceleration, I'm going to use dv, or dx dot, dt. So if I integrate, then, and turn upside down, of course, because I want it with respect to dx dot. And I'll have minus 1 on k, the integral of dx dot over x dot, going from the initial velocity, same as a normal projectile motion question, that hasn't changed because we haven't started. It's initial velocity, so the air resistance hasn't taken effect. So it's still u cos alpha, going to some random velocity that we're trying to get a formula for. But look at what we're integrating. It's just dx on x, if you like. Log. So we know that's going to be log. So subbing in, I'll get log of x dot minus log of x u cos alpha. Or we could have written that as one complete log using our log laws. Right? We remember we're trying to get x dot the subject. So I've got to undo the log. Before I can undo the log, multiply by the minus k. And there's my minus kt I'm looking for. Undo the log, exponentialise. There's the e to the minus kt. Multiply by the bottom of the fraction. We've got our answer. Yeah, we've got our answer. Verify. This is where I didn't read the question. Because it simply said verify. I actually went and proved it. They said a little bit of time. But verify means I could just show hey, this works. Like the simple harmonic motion questions where they simply say, show that this is in simple harmonic motion. You just differentiated and went, oh, look, it satisfies. I sort of went the long way about it. And said, all right, I'm going to use dy dot dt is equal to minus ky dot minus g, and then integrated, similar sort of expression. Substitute in really the same steps as the last one, but it's just that the function's slightly different. And I end up with the final answer. But as I say, that's probably the long way to go. The quicker way would have been, I guess, to differentiate that with respect to time, which is not hard because, again, all these things are basically constants, and show it's satisfied that acceleration equation that they gave us. That probably would have been quicker. All right, value t, particle reaches maximum height. The laws of physics have not changed. Maximum height is still going to happen when the vertical velocity is 0. So we want to solve that equation. All right. And you might be looking at it and thinking, what? See, the advantage, I guess, because I did do it the long way, is I already had an expression to work out time in terms of the integral. And I'm saying I'm going from initial velocity of u sine alpha up to a velocity of 0. So subbing those in, and I get my answer in just a couple of lines. So whilst I went the long way about part B, it actually had a nice little advantage to part C. Right? What is the limiting value of the horizontal displacement? The limiting value of the horizontal displacement. Well, I need to get an expression for horizontal displacement then. We, back in part A, I think it was, worked out this expression here. X dot is equal to u e to the minus kt. So I've got velocity in terms of time. I want to get displacement. So velocity to displacement, let's integrate again. And I want the limiting displacement. So I'm going from a time of 0 up to a time of infinity. But of course I can't substitute infinity in, and that's why at the front here I've put the limit as t approaches infinity. That's the limiting velocity. Or displacement, sorry, in this case. So I just still integrate as normal, but I leave this to be t. Oops, this integral is written slightly wrong. That should have been t at the top, not infinity. Because I can't sub infinity in, but I can sub t in and say, as t approaches infinity. But I fixed that up, you'll see in the next line there. Okay, so there's the expression we're trying to find the limit of. Again, looks horrible, but really all I'm interested in is that exponential, because that's where t is. So what do we got? We got e to the power of a negative, e to the negative x, if you like. Imagine that graph. T approaches infinity. What's the graph doing? Yeah, it's coming close to the axis. So that exponential part will approach 0. So therefore, I'm just left with u cos alpha over k. And there's my answer. That would be the limiting value of the horizontal displacement. Nasty question, eh? But lovely at the same time. Okay, so whole heap of just different questions to look at. As I said to you, we'll spend the rest of the week just looking at this sort of stuff. I won't do any more